Okay, let me. So that's lecture 3, chapter 7, systems of first order differential equations. I was some so part 1 is it's Eigenvectors. Okay, so let's try to prove them. Oh, it's very easy, it's not that hard. So let me start with fact 1. It's just so A symmetric means that A transpose is A. And eigenvalue equation, eigenvalue problem is something like this. Now, when I say real, it means that, remember I solved a problem last time, an eigenvalue problem with complex eigenvalues and complex eigenvectors. So it can be complex. Now, to show that lambda is real, it suffices to show that lambda bar equals lambda. Why is it? If A plus BI equals A minus BI, then B equals minus B, then 2B is 0, that gives me B is 0. So if B is 0, it is a real number. So that's what I am going to show. So let me erase this. Well, this A is a real matrix. It means that we have the entries are real numbers. But V and lambda can be complex. So this, if I find the conjugate of them like this, conjugate lambda, conjugate V, conjugate, that also applies. If I can just conjugate all of them and the equation holds. Now A conjugate is A because that's real. So I have A, in fact, V, should I write this like? So let's say this. Yeah. Let's put vector on top of this conjugate and V vector. Okay. Now if I transpose both sides, transposing both sides, this side will be V transpose A transpose, and this side will be, well, lambda is lambda, that stays, and V bar transpose. Now I multiply both sides by V itself. So if I multiply by V from the write V A and A transpose A. So I just write in here. A V equals lambda bar V transpose V. Okay? And V is the vector. Now let's look at this thing here. Well, this is in fact the magnitude of vector V as a complex vector. So let's, if V is a complex vector, V, a complex vector, then the magnitude of V is, well, let's write square because that's in fact square. This is Z1 squared, Z2 squared, Zn squared. Now what is Zn, Z1, Z2? In fact, V is a complex vector, so it is something like this, Z1, Z2, Zn. Right? So that's the length of this plus length of this plus length of this, or magnitude, 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 and so on. Now, about Z1 squared, we know that this is in fact Z1 bar Z1. This is Z2 bar Z2, and so on, Z n bar Z n. But this is something, this is in fact this thing, V bar transpose times V as vector. Right? This is like two vectors multiplied. It is this times this. So I can write somewhere here that the magnitude of, well, let's open a box here, magnitude of V as a complex vector is square root of V or transpose V. Remember, for real vectors it's something similar, except there is no bar. It's just V transpose V. Okay? So let me erase this green part and continue with what I have here. So that is, in fact, magnitude of V squared. What is this? This is right here. That is lambda V. So the left side will be lambda V. Oh, gee, I forgot the transfer. V, well, let me write with blue. I guess blue is much better. You can see that. Transpose this V. On the other side, I have lambda V squared. This is also V squared, lambda bar. So that is lambda V squared equals lambda bar V squared. V is not zero because V is an eigenvector, and we said we don't want zero eigenvector. So V and V cancel out, and I will get lambda equals lambda bar, which tells me that lambda is real. Okay, so let's go back and check it again. So this is the assumption, and also this. I used, I conjugated both sides, and when you conjugate, nothing happens, just put conjugate on top. And So everything inside is conjugated, and this one is real. So conjugate is the same. So this one doesn't change. And then I transpose both sides. This side transpose, it flips. So this is V transpose, A transpose. This side is simply, this is just a vector, so that one is transposed. And then I multiply from the right by V itself. So V transpose V bar transpose times V is the magnitude of V squared. And on this side, I use this fact here. So I use this fact here that this is lambda V, and well, lambda is just a constant. We can write it first, then it is V bar transpose times V, and this is the vector in fact. So and that is again magnitude of V squared. That's another thing. In fact, magnitude of V1 and V are the same. So I have lambda equals lambda bar, which means that lambda is a real number. Now, if you look carefully from here to here, this is one of the crucial steps. I use the fact that A is symmetric. AT is A. I use that it is symmetric. So that is where the symmetry comes in as a crucial thing in this proof. So now fact 2 is well, this also proves that eigenvectors are real. When you solve, you have real numbers, and then you solve for eigenvectors, you have real systems of equations, homogeneous systems with real coefficients. And everything is real. So when you solve it, you will get real numbers. So the eigenvectors are also real. Okay, let's see. Let me see what fact 2. Now that we know they are real, how can we prove that they are in fact orthogonal? What does orthogonal mean? So this fact 1 also implies that eigenvectors are real. Okay, so when you solve for eigenvectors, you just have a system of equations with real coefficients, so you will get real solutions. So let's say fact 2 eigenvectors are orthogonal. So let's say A V1 is lambda 1 V1. But this one is a simple assumption. Eigenvectors are orthogonal for corresponding to distinct eigenvalues. Not the same, corresponding to distinct eigenvalues. The interesting thing is that you can in fact extend, even if they are not distinct, you can extend that to an orthonormal basis, but that's not the point. So if I have distinct, so let's write two distinct equations, V2 lambda 2 V2, and let's assume that lambda 1 is not equal to lambda 2, okay? So these are two equations, and so let's transpose this one, okay? So let's transpose this first one, both sides, and I know that they are real, so the transpose will be V1 transpose A transpose. On this side I have lambda 1 V1 transpose. Okay? A transpose is A, so that is in fact V1 transpose A is lambda 1 V1 transpose. Now I multiply from the right by V2. So I have V1 transpose A, V2 is lambda 1 V1 transpose V2. Okay. Now, A V2 is lambda 2 V2. So I just write lambda 2 V2 here, and lambda is just a constant, just so this is lambda 2 V2. So I have lambda 2 V1 transpose V2 equals lambda 1 V1 transpose V2. Okay. So if I move them to one side, say to the left side, say I have lambda 2 minus lambda 1 times V1 transpose V2 is 0. This is not 0. This is not 0, so this is 0. V1 transpose V2 is 0. And remember, this is what? This is the dot product. So that's the dot product in Rn. So that is V1 dot V2 is 0. So it means that V1 is orthogonal to V2. And remember, these are all real, so there is no complex. And in fact, the first fact just throws away complex numbers, and you can just stay in like Rn if that is an n-dimensional in my n matrix. So that's it. That's an amazing fact, because I will show you why this is interesting. So why is it interesting to have something like this? Now, the other thing I'm not going to prove, but you can extend this, even if the eigenvalues are not this thing, you can extend it to an orthonormal basis or orthogonal basis. So let me erase all these things. What is an orthonormal basis? Suppose I just take Rn. Take Rn. If I have n vectors that are orthogonal to each other, well, a vector is not orthogonal to itself, okay? So orthogonal to each other, then if it is n exactly n, that makes a basis for Rn. So take Rn. Let V be, say, not V, we usually use S, right? So S be this vector V1, V2, Vn, such that Vi dot Vj is 0 for I not equal to j. Okay, so that is orthogonal. Then I claim that this is a basis. Claim S is a basis for Rn. Now, first of all, it is n. So it has n vectors. So the only thing I have to prove is that they are linearly independent. If we prove that they are linearly independent, then because they are n vectors, they make a basis for R. Okay, so if I can just prove that they are linearly independent because they are n, then they make a basis for R. So let's see if we can prove that they are linearly independent. So let me erase this thing. in linear independence, so I'll say alpha 1 v1 plus alpha 2 v2 alpha m vn equal to 0. Let's multiply this by vj or vr. So dot with vi, say. Okay, so I have alpha 1 v1 dot vr, alpha 2 v2 dot vr, up to dot alpha n, another alpha I vi dot vi and plus dot alpha n vn dot vi, and that is 0 because dot 0 dot vi is 0. Okay. This is 0, remember the orthogonal, except this is the length of vi squared, and I assume that vi's are not 0, so I should have said that, and none of them is 0. None of them is 0 vector. So, in fact, if any 0 vector is in that set, that's not linearly independent. Remember, that was like a theorem. And so I have alpha I, and it's 0. So what happens? Everything is 0 except this one. So I have alpha I, vi squared is 0. This guy is not 0. So this tells me that alpha I is 0 for all I from 1 to n. Okay, so a linear combination, a 0 linear combination only gives me 0 for the alpha i's. That shows that S is linearly independent. So that makes a basis for Rn. I can say that Rn is now span of S. Okay. Now I can make this into what we call an orthonormal basis. So orthonormal means that, well, let me erase all these things. And orthonormal is simply, it means that they are normalized, which means they all have unit magnitude. So S is an orthonormal basis if vi is 1 for all I, and vj is 0 for I not equal to j. Okay. Now, what is special about this orthonormal? If I write down a matrix A, so well, let me call it something V, matrix, yeah. So let matrix V be these vectors as column vectors. So these are column vectors. Remember, we use column vectors. Okay. Let's see what happens to V transpose. So V transpose is this. V1 transpose, V2 transpose up to Vn transpose. Okay? So let's see what happens when we multiply V transpose by V. So that is V1 transpose, V2 transpose, Vn transpose, times V1, V2, Vn. So, what is the ij entry of this. So if I set this to be Aij, well, I know this is n by n. If that is n, no, that's n. So n by n, then Aij is simply Vi transpose dot Vj. Remember how we multiply matrices? Row, column, row, column, row, column, row, column, and so on. But this is 0. If I is not j, and it's 1 if I equals j. Okay? So this matrix is simply In. It has 1s in the diagonal. The diagonal terms, this is diagonal. Diagonal terms are 1, and off diagonal terms are 0. So this, in fact, let me write here. How should I? So V transpose V is In. Also, the same way, because that's the same, so it's also In. So this tells me that V transpose equals V inverse. So we don't have to find inverse of a matrix like this. If I have a matrix with orthonormal, say, columns, then I don't have to inverse that. The inverse is simply its transpose. That's just amazing about orthonormal matrices or orthonormal basis for Rn. Okay. So let me erase this and tell you why I'm just doing all these things. So I said if I have a symmetric matrix, and I find eigenvalues and eigenvectors, then eigenvectors can be extended to an orthonormal set. And how many eigenvectors do I have? If it is n by n, gives me n orthonormal vectors. Okay, so that gives me n orthonormal eigenvectors. Eigenvectors. Okay. When I have n orthonormal eigenvectors, then the eigenvectors of A span Rn. Okay, so Rn will be span of eigenvectors of A. That's n and they're orthonormal, so that's a basis for Rn. So that is basis for Rn. Another thing is, if I gather them in a matrix like this, VI's eigenvectors of A, then V inverse is V transpose, right? And remember, I have orthonormal eigenvectors. Orthonormal. So, if I have an n by n symmetric matrix and I find eigenvectors, then those eigenvectors span Rn. So that's amazing, because if you want to find a set of bases other than EIs for Rn, it's not easy. So you can start with something and then you have to go on and on and on, find n, say, vectors that are mutually orthogonal, perpendicular, and well, it's easy to normalize them, but doing that is not easy. We will, in fact, it's out of, I mean, it's not for this class, but you can do that using an algorithm called the Gram-Schmidt process. But anyway, so if you just pick an n by n symmetric matrix and find eigenvectors, then you have the basis for Rn, orthonormal basis for Rn. Now, there's another thing which I have to discuss here, and then we continue with differential equations. Another thing is diagonalization. First of all, I go back to that. If I have A symmetric, then I will get n orthonormal eigenvectors. Well, I just proved that if I have any orthonormal eigenvectors or vectors, say, they are linearly independent. So, eigenvectors of A when it's symmetric are linearly independent. Now, this diagonalization happens when I have linearly independent eigenvectors. So, if A is n by n has linearly independent eigenvectors, I'm not saying orthonormal. Most nice matrices have this property, but not orthonormal, there's no way. And this is not symmetric, I'm just any n by n. But I'm assuming that it has linearly independent eigenvectors. Well, you can ask, okay, what does it mean, linearly independent, if they are, say, complex? Well, I know, it's the same thing, just a linear combination of them equal to 0 should give me 0 coefficient. So, anyway, so now let's write down. So I have A vi, if that's an eigenvector, is lambda I vi. Okay? So let's put them in a matrix format. So I have A v1, A v2, and A vn as columns of a matrix. And on this side, I have lambda 1 v1, lambda 2 v2, lambda n vn as columns of this matrix. So I have column, 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 and so on. This is very easy to see that this is in fact A times v1, v2, vn. But this side is different. This side will be v1, v2. You can check yourself and see this happens. Now this is not times on this side, it will be times this on this side. Lambda 1, lambda 2, dot, 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 lambda n, 0, 0. So it is multiplied by a diagonal matrix with lambdas in the diagonal. Okay, so if I denote this, say, by V, and then this is also V, I have come up with an interesting formula. So, where should I write this? Let me erase this thing. So I found that A times this V, this special matrix, is V times D. Now these vectors, I assume that the eigenvectors are linearly independent. Well, if they are linearly independent, they make a basis for Rn, in fact, because they are n. And we saw that when A is symmetric, that happens. But the problem is maybe they are not real. Maybe they are complex values. So anyway, if they are real value, then. Now, I assume that they are linearly independent. So we can invert this V. We can invert V. So if I can invert V, so if I multiply this by V inverse on this side, this gives me two, in fact, things. One is V inverse A, V is V inverse V D, which this is I, so this is D. And also if I multiply this on this side by V inverse A, V inverse is V D V inverse. But this is A, so this is equal to A. So I have found this. I have found that A is V D V inverse, which gives me D is V inverse A V. So this is, we say that diagonalization, or also it's known as spectral decomposition. So this is A. What do we have here? It is a simple diagonal matrix with entries being lambda i's. Remember, I said lambda i's are unique, but this V or the VI's eigenvectors are not. You can just multiply any one of them by any constant, and that's again an eigenvector. So this middle one is unique. The D is unique. Now, what is it good for? One place that it is used, first of all, this is used in differential equations when we have forcing function. So one method of solving a system of equations with forcing functions is using this, which I probably won't do. Let me see if I have time to do it. But that's one way. In fact, in your textbook, it does have that method. But there's another thing which, if suppose I want to raise this to power m, some m, let's say m. So if I want to raise this to power m, so I have V D V inverse, V D V inverse, and this times itself n times. So if I remove parentheses, this and this is I. So I will end up with V, then D. I have D to power m and V inverse. Isn't that interesting that raising this to power m is simply raising D to power m and just multiplying from on this side by V, on this side by V inverse. Let me show you how to raise D to power m. You might have guessed how that happens. So if I have, say, D is in fact a diagonal matrix, lambda 1, lambda 2, lambda n, 0, 0, D to power m will be 1. If you multiply 2 times and 3 times, you will see that lambda 1m, lambda 2m, lambda n, 0, 0. So that's very easy. Just raise this to power diagonals, power m, and that's it. That's all you have. It also tells me something else, that am, eigenvalues of am are in fact this, lambda I to power m. And eigenvectors are the same as A. Okay, so there's one place it is used when you raise a matrix to some power. It's simply doing that. And as I said, it's also used in solving systems of differential equations when you have forcing functions. And now this is also, well, if I have a symmetric matrix, what happens? If I have asymmetric